The morning air hung heavy over Kasumigora Naval Air Station on a February day in 1945. Lieutenant Toyoda Takago stood beside the damaged American fighter, its distinctive inverted gull wings bent awkwardly where they'd absorbed the impact of an emergency landing in a nearby field. The fabric patches covering holes in the wing gleamed white against the dark blue paint, improvised repairs made with materials salvaged from other wrecked Corsairs scattered across the home islands. But it was what lay beneath the cowling that commanded Toyoda's attention. The Pratt & Whitney nameplate caught the weak winter sun, and beneath it, stamped into metal with American precision, were the specifications that would confirm what many in the Imperial Japanese Navy had begun to suspect, but few dared to speak aloud. The war was already lost. The Vought F-4U Corsair represented more than captured enemy equipment. It was physical evidence of an industrial capacity so vast, so technically advanced, that it rendered Japan's entire aviation philosophy obsolete. Within weeks, Japanese engineers would fire up that massive 18-cylinder radial engine for the first time, and in the thunder of 2,000 horsepower, they would hear the death knell of the Zero fighter that had once dominated Pacific skies. This is the story of that discovery, not of a battle lost, but of an illusion shattered. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. To understand the magnitude of what Japanese aviation specialists found when they examined that captured Corsair, one must first understand the mythology that had sustained Japanese naval aviation since the outbreak of the Pacific War. The Mitsubishi A-6M0 fighter, designated the Type 0 carrier fighter when it entered service in July of 1940, had been designed around a specific philosophy: achieve superior range and maneuverability through radical weight reduction. The result was an aircraft that weighed just 2,796 pounds empty, powered by a Nakajima Sakai 12 engine, producing 925 horsepower. In the war's opening months, this philosophy appeared vindicated by overwhelming success. Over the skies of Pearl Harbor, Malaya, the Philippines, and the Netherlands East Indies, Zero pilots achieved kill ratios that shocked Allied commanders. American pilots flying the Grumman F-4F Wildcat found themselves outturned, outclimbed, and outranged by an enemy fighter they had been assured was inferior. Japanese propaganda celebrated the Zero as the embodiment of Yamato Damashi, the Japanese spirit, claiming that superior training and warrior ethos had produced an invincible weapon. But the Zero's advantages came at a terrible price, one that would only become apparent as the war progressed. To achieve its phenomenal range of nearly 2,000 miles and its extraordinary maneuverability, Zero designers had eliminated virtually all pilot protection. There was no armor plating behind the cockpit, no bulletproof glass, no self-sealing fuel tanks. The aircraft was built from an advanced aluminum alloy developed specifically for weight savings, and every possible gram had been shaved from the airframe. Japanese naval doctrine in the late 1930s had called for a fighter capable of operating over vast Pacific distances while maintaining air superiority over enemy formations. The Imperial Japanese Navy's requirements, issued in 1937 to both Mitsubishi and Nakajima, specified a maximum speed of 310 miles per hour, a climb time to 9,840 feet of 3.5 minutes, and an endurance of 6 to 8 hours with drop tanks. These specifications bordered on the impossible given the engine technology available at the time. Mitsubishi's chief designer, Horikoshi Jiro, and his team achieved these seemingly contradictory requirements through ruthless weight optimization. Every component was analyzed, redesigned, and manufactured to minimize mass. The result was an aircraft that handled like a dream at low speeds, could outmaneuver any opponent in a turning fight, and possessed range capabilities that allowed Japan to project air power across the vast distances of the Pacific theater. The first prototype, designated A6M1, flew on April 1, 1939, powered by a Mitsubishi Zuisei 13 engine producing 780 horsepower. Performance fell short of requirements. But when the third prototype flew in January 1940 with the more powerful Nakajima Sakai 12 engine, the aircraft exceeded its specifications. By July 1940, the Zero was officially adopted as the Type 0 Carrier Fighter Model 11, named for the imperial year 2600. Combat debut came in China during the Second Sino-Japanese War, where Zeros operating from captured airfields near Shanghai provided long-range escort for bombing missions deep into Chinese territory. Chinese and Soviet pilots flying Polikarpov, E-15 seconds and I-16 seconds found themselves completely outclassed. Zero pilots racked up impressive victory claims with minimal losses, creating an aura of invincibility that would follow the aircraft into the Pacific War. When war erupted on December 7, 1941, approximately 328 A-6M fighters were in frontline service with the Imperial Japanese Navy. These aircraft spearheaded Japan's assault on Allied positions across the Pacific. At Pearl Harbor, Zeros from 6 aircraft carriers provided fighter cover for the attacking bombers and dive bombers, strafing American aircraft on the ground and engaging the handful of American fighters that managed to get airborne. In the Philippines, Malaya, and the Netherlands East Indies, Zeros quickly established air superiority over Allied defenders. Allied intelligence had received warnings about the Zero's capabilities from reports emerging from China, but these were largely dismissed. American and British aviation experts refused to believe that Japan, a nation they considered technologically inferior, could have designed and produced a fighter superior to their own frontline aircraft. This underestimation would cost Allied pilots dearly in the war's opening months. The psychological impact of the Zero on Allied airmen cannot be overstated. Pilots who had trained to believe in Western technological superiority suddenly found themselves flying aircraft that were demonstrably inferior to their Japanese opponents. The F-4F Wildcat, the primary American carrier fighter in 1942, was more rugged than the Zero and could take more punishment, but it was slower, less maneuverable, and had a significantly worse rate of climb. British Brewster Buffaloes were even more outmatched. Lieutenant Commander John S. Thatch, commanding officer of Fighting Squadron 3, witnessed firsthand the Zero's superiority during the Battle of Midway. His assessment was blunt. American fighters were at a severe disadvantage in nearly every performance category. Thatch developed the Thatch Weave, a defensive tactic that used mutual support between pairs of Wildcats to counter the Zero's turning advantage, but this was a tactical response to a fundamental technological deficit. Japanese naval aviation doctrine emphasized intensive training to maximize the potential of their aircraft. Pilots typically accumulated 800 to 900 flight hours before assignment to carrier squadrons, with specialized training in carrier operations adding several hundred more hours. This rigorous preparation, combined with the Zero's performance advantages, created an elite force that dominated the Pacific skies throughout 1942. But cracks in the foundation were already appearing. The Sakai engine, while reliable and fuel-efficient, was fundamentally limited in power output. The 14-cylinder radial produced 925 horsepower in the Model 21 variant, and even the improved Sakai 21 engine introduced in 1941 could only manage 1130 horsepower using a 2-speed supercharger. This power limitation meant that any significant increase in armor, fuel capacity, or armament would severely degrade the Zero's performance. Japanese engineers were acutely aware of these limitations. The Aviation Technical Research Laboratory at Tachikawa, operated by the Imperial Japanese Army, and the Yokosuka Naval Air Technical Arsenal, responsible for Imperial Japanese Navy aviation research, both studied captured Allied aircraft when opportunities arose. In the war's early months, these opportunities were abundant as Japanese forces overran Allied airfields throughout Southeast Asia and the Pacific. Among the captured aircraft examined were Curtiss P-40 Warhawks, Brewster Buffaloes, and eventually several Boeing B-17 Flying Fortresses. Japanese engineers were consistently impressed and occasionally disturbed by what they found. Designer Kikuhara Shizuo, who had originated the Kawanishi H-8K flying boat, examined a captured B-17 and noted his surprise at how American designers had perfected the bomber's subsystems to require minimal cockpit controls. The aircraft's construction quality and integration of complex systems represented a level of mass production sophistication that Japanese industry struggled to match. Lieutenant Toyoda Takago, working in the Japanese Navy's Foreign Technology Program, reported that most captured aircraft were sent by the Army's field recovery teams, with the Navy receiving copies of reports and occasionally borrowing aircraft for testing. The single Navy team Toyoda recalled dispatching went to Burma to study a crashed Mosquito light bomber. But aircraft recovered in the southern areas or crash sites within the Empire's defensive perimeter, including Okinawa, were thoroughly examined at Yokosuka's technical facilities. When an F-6F Hellcat was recovered after American raids on Okinawa in October 1944, Yokosuka's specialists noted its extremely strong construction. This would become a recurring theme in Japanese technical intelligence reports. American aircraft were built to standards of structural strength and protection that Japanese designers had sacrificed in pursuit of performance. The philosophical difference was stark. Japanese aviation had bet everything on the superiority of the lightweight, highly maneuverable fighter flown by superbly trained pilots. American aviation doctrine emphasized ruggedness, firepower, and the ability to absorb battle damage qualities that reflected an industrial economy capable of producing aircraft in vast numbers. The contrast extended beyond mere construction, techniques. Japanese pilots often spoke with a mixture of admiration and frustration about engaging damaged American aircraft that simply refused to go down. A Zero pilot might pour multiple cannon shells and dozens of machine gun rounds into a Wildcat or Thunderbolt, only to watch it limp away trailing smoke. Meanwhile, a single burst from American half-inch machine guns could set a Zero's unprotected fuel tanks ablaze, turning the lightweight fighter into a flaming coffin for its pilot. By mid-1943, the production statistics were becoming undeniable even to Japanese leadership. American aircraft production had reached levels that Japanese planners had considered impossible. The United States was producing more aircraft in a month than Japan could manufacture in a year. More troubling still, these aircraft represented not just numerical superiority, but technological advancement. New American fighters entering service, the F-4U Corsair, the F-6F Hellcat, the P-38 Lightning, and the P-47 Thunderbolt, all shared certain characteristics. They were fast, heavily armed, well-armored, and powered by engines producing 1,800 to 2,000 horsepower or more. The Corsair, in particular, represented everything the Zero was not. Where the Zero was delicate, the Corsair was brutally robust. Where the Zero relied on maneuverability, the Corsair relied on speed and firepower. And where the Zero's engine produced 1,130 horsepower in its most powerful variant, the Corsair's Pratt & Whitney R2000 800 double Wasp engine produced 2,000 horsepower as a baseline, with later models pushing even higher. The R2800 was America's first 18-cylinder radial engine, a massive two-row design with a displacement of 2,804 cubic inches 46 litres. Development had begun in 1936, and the engine first ran in 1937. It represented a fundamental difference in engineering philosophy from the Japanese approach. Rather than optimize for weight and fuel efficiency, Pratt & Whitney engineers had designed for power, reliability, and the ability to absorb combat damage. The engine weighed over 2,000 pounds dry heavier than an entire Zero airframe without its engine. When test pilot Lyman A. Bullard Jr. first flew the XF-4U-1 prototype on May 29, 1940, the Corsair became the first single-engine American fighter to exceed 400 miles per hour in level flight. This achievement, accomplished in October 1940 during Navy testing, represented a quantum leap in fighter performance. The combination of the R2000 800 engine and the Corsair's distinctive inverted gull wing design created an aircraft that could dive away from any Japanese fighter, deliver devastating firepower with its 6 half-inch machine guns, and absorb battle damage that would have destroyed a Zero. Japanese intelligence officers, tracking American aviation developments, noted these advances with growing concern. Reports filtering back from frontline units consistently described encounters with American fighters that possessed speed advantages Japanese pilots could not counter. The classic zero tactic of using superior maneuverability in turning fights became increasingly irrelevant when American pilots simply refused to engage in that type of combat. Instead, they employed boom and zoom tactics, diving from altitude, making high-speed firing passes, and climbing away before Zero pilots could respond. This tactical evolution reflected not just better aircraft but also improvements in American pilot training and doctrine. While Japanese training programs remained excellent for those who completed them, attrition was steadily eroding the pool of experienced instructors and veteran combat pilots. American training programs, by contrast, were expanding rapidly, producing thousands of competently trained pilots who learned tactics specifically designed to exploit the Zero's weaknesses while avoiding its strengths. The Solomon Islands campaign became a grinding war of attrition that Japan could not sustain. Marine and Navy pilots flying from Guadalcanal's Henderson Field and from carrier task forces systematically destroyed Japanese air groups attempting to reinforce or attack Allied positions. The famous Black Sheep Squadron, VMF 214, led by Major Gregory Boyington, typified this new breed of American fighter pilot. Boyington himself claimed 22 kills flying Corsairs, using tactics that maximized the aircraft's speed and firepower advantages while avoiding prolonged turning engagements. By February 1943, when the first Corsairs deployed to Guadalcanal with VMF 124, Japanese pilots were already reporting encounters with this new American fighter that they called Whistling Death, a name derived from the distinctive high-pitched noise made by air flowing through the Corsair's air intakes during high-speed dives. The sound alone became psychologically devastating, announcing the arrival of an opponent that Japanese pilots increasingly feared. The Corsair compiled an 11-to-1 kill ratio during World War II, a statistic that reflected not just superior performance, but the growing gap between American and Japanese aviation capabilities. Each new American aircraft type that appeared over the Pacific represented another iteration of technological advancement backed by seemingly unlimited industrial production. Japan, meanwhile, struggled to produce even modest numbers of improved fighters while maintaining production of existing types. The opportunity to examine American fighter technology intimately came not through brilliant intelligence operations, but through the simple mathematics of aerial combat attrition. By early 1945, American carrier task forces were operating within striking distance of the Japanese home islands with near impunity. On February 16th, 17th, and 25th, 1945, massive carrier raids struck targets around Tokyo Bay, Yokosuka Naval Base, and surrounding areas. Navy records document multiple Corsair losses during these operations, aircraft damaged by anti-aircraft fire, suffering mechanical failures, or simply running low on fuel after extended combat operations over hostile territory. 1 F4U-1, Bureau number 57251, from the USS Essex, made an emergency landing in a field near Tsuchiura City in Ibaraki Prefecture on February 25th. The aircraft came down hard but largely intact. Its landing gear collapsed, wings bent but not broken, fuselage crumpled but not catastrophically destroyed. The pilot, following standard procedure, attempted to destroy classified equipment and set fire to the aircraft before evacuation or capture. But whether due to the pilot being injured, captured too quickly, or the aircraft's fuel-soaked state, preventing complete destruction, the Corsair survived in recoverable condition. Japanese Army units secured the crash site within hours. Initial reports went up the chain of command to the Aviation Technical Research Laboratory at Tachikawa, the Imperial Japanese Army's primary aviation research facility. Simultaneously, because the aircraft had crashed near Kasumigara, home to the Naval Aviation Technical Training Institute and one of Japan's most important aviation facilities, the Imperial Japanese Navy claimed jurisdiction. What followed was typical of the poor coordination that plagued Japanese military research. Both services wanted the aircraft, both dispatched teams to examine it, and ultimately the Navy, given its proximity and the aircraft's carrier origins, took possession. The damaged Corsair was transported the short distance to Kasumigara Naval Air Station. There, in hangars that had once housed British training aircraft from the Semple mission of 1921, Japanese engineers began their examination. Lieutenant Toyoda Takago was among those assigned to document and analyze the captured fighter. The Navy's approach to captured aircraft study involved meticulous documentation, measurements, photographs, material samples, and detailed technical drawings of every component and system. The initial visual inspection alone revealed troubling disparities. The Corsair was massive compared to a Zero. Its empty weight exceeded 7,500 pounds, nearly 3 times that of a Zero. The fuselage was substantially built with heavy structural members. The cockpit featured thick armor plating behind the pilot's seat and bulletproof glass in the windscreen. The fuel tanks, when examined, proved to be self-sealing, a technology that Japanese designers had experimented with but never successfully implemented in production aircraft due to weight and complexity concerns. But it was the engine that commanded the most attention and provoked the most profound dismay. The Pratt & Whitney R 2800 Double Wasp represented a level of engineering sophistication and manufacturing capability that Japanese industry could not replicate. The engine displaced 46 litres, more than 3 times the displacement of the Sake engine. It featured 18 cylinders arranged in 2 rows of 9, each cylinder precisely machined to tolerances measured in thousandths of an inch. The supercharger system was vastly more complex than anything in Japanese service, using a 2-stage design that maintained power output at high altitudes, where Japanese fighters gasped for air. Japanese engineers carefully documented every component. The cylinders were forged rather than cast, allowing for higher compression ratios and greater power output. The crankshaft was a masterpiece of metallurgy, designed to handle stresses that would have shattered components in Japanese engines. The ignition system used dual magnetos for redundancy. The carburetor was a sophisticated automatic unit that adjusted fuel mixture based on altitude and throttle position. Every system reflected a design philosophy that prioritized reliability, maintainability, and combat survivability over weight savings. When engineers examined the engine's data plates and cross-referenced them with the limited intelligence available on American aviation, the full picture emerged. This particular R2800 variant, likely the -8 model used in early Corsair production, was rated at 2,000 horsepower at 2,700 RPM. Later variants could produce 2,250 horsepower with water injection for emergency war power settings. By contrast, the most powerful engine in Japanese naval service, the Nakajima Sakai 21, produced 1,130 horsepower, barely more than half the American engine's output. The implications were staggering and undeniable. American designers had not achieved superiority through superior aerodynamics or revolutionary design concepts. They had achieved it through brute force application of industrial capacity and engineering resources. The Corsair did not need to be lightweight because American factories could build engines powerful enough to push a heavily armed fighter to speeds exceeding 400 miles per hour. The aircraft did not need to sacrifice pilot protection because American metallurgy could produce armor plate in quantities sufficient to protect every fighter rolling off the production line. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Recovery teams discovered evidence that Japanese engineers had attempted to make the captured Corsair airworthy. Fabric patches covered damage to the wing where metal panels had been torn or punctured during the crash landing. These patches came from other wrecked American aircraft by February 1945. Wreckage from multiple Corsair crashes littered the Tokyo area. Bureau numbers from at least 2 other F-4s were documented in Japanese records from this period, suggesting that engineers were cannibalizing parts from multiple wrecks to create one potentially flyable aircraft. The fabric repairs represented desperate improvisation. Japanese engineers lacked the specific aluminum alloys used in corsair construction and certainly did not have spare parts or proper repair procedures. But they attempted repairs anyway, covering structural damage with fabric doped to tautness, reinforcing from the inside with whatever materials were available. The goal was clear: get this aircraft into the air, test its performance firsthand, and perhaps glean insights that could inform Japanese fighter development. Whether they succeeded in flying, the repaired Corsair remains uncertain. No definitive Japanese documentation of a successful test flight has survived, though the presence of fabric repairs and evidence of engine work suggests they got further than mere static examination. American forces recaptured the aircraft near Kasumigara in 1945, after Japan's surrender. The presence of those improvised repairs indicated Japanese engineers had progressed beyond study to attempted restoration. What is certain is that the mere presence of this aircraft at Kasumigara represented a teaching moment far more powerful than any intelligence briefing or technical report. Here was physical proof that every claim about American industrial might was true. Japanese propaganda had assured the population and military that American products were inferior, mass-produced junk built by a soft, materialistic society. The Corsair demonstrated the opposite. American industry produced aircraft built to standards Japanese factories could barely imagine, powered by engines whose sophistication exceeded anything in the Japanese arsenal, in quantities that dwarfed Japan's total production. The timing of this discovery, February 1945, made it particularly bitter. Japan had already lost the Marianas, severing the homeland from resource-rich territories in Southeast Asia. American submarines had reduced merchant shipping to a trickle. Strategic bombing of Japanese cities was intensifying. Aircraft production was declining due to shortages of aluminum, fuel, and skilled labor. The Corsair represented everything Japan lacked and could never hope to match: abundant raw materials, advanced industrial processes, skilled engineering, and effectively unlimited production capacity. Yokosuka Naval Air Technical Arsenal specialists who examined the Corsair's construction were particularly struck by the quality of materials used. The aluminum alloys were superior to Japanese equivalents, offering better strength-to-weight ratios and improved fatigue resistance. Fasteners were standardized and precision-made. The electrical systems used better insulation and more reliable components. The hydraulic systems showed sophisticated sealing technology and precision machining that Japanese industry struggled to replicate even in laboratory conditions. The aircraft's armament told another story of American abundance. 6 Browning M2 heavy machine guns, each capable of firing 850 rounds per minute of half-inch ammunition, gave the Corsair devastating firepower. Japanese fighters typically mounted 2 20mm cannons and 2 7.7mm machine guns, powerful enough, but limited by ammunition capacity and reliability issues. The Corsair's guns were belt-fed, allowing for sustained fire. Each gun had 360 rounds of ammunition as standard load, giving the pilot over 20 seconds of continuous firing time across all 6 guns. But beyond the armament itself was the quality of the ammunition. American half-inch rounds used better propellants, more reliable primers, and superior projectile design. They were manufactured to tighter tolerances, reducing jamming and misfires. Japanese ammunition production, by contrast, suffered from declining quality control as the war progressed. Pilots increasingly reported gun jams and ammunition failures that often proved fatal in combat. The Corsair's fuel system revealed another dimension of American technical superiority. The self-sealing tanks used a rubber compound that swelled when exposed to aviation gasoline, automatically sealing bullet holes. Japanese engineers understood the principle. They had examined self-sealing tanks in other captured aircraft, but lacked the specific rubber formulations and manufacturing processes to produce them at scale. The few Japanese aircraft fitted with experimental self-sealing tanks suffered significant weight penalties and reduced fuel capacity, negating much of the benefit. Even the Corsair's basic construction revealed telling details. Panel fits were precise, with consistent gaps and flush riveting throughout. The cockpit layout was ergonomically designed with controls positioned for easy access during high-stress combat. The canopy provided excellent visibility, though early Corsairs had struggled with over-the-nose visibility during carrier landings, a problem that led to the aircraft initially being deployed primarily with land-based marine squadrons rather than carrier navy. Squadrons. Japanese engineers examining the gun sight found it to be a sophisticated reflector design with gyroscopic stabilization. American pilots could track and hit targets during high-speed maneuvers with accuracy that Japanese pilots, using simpler ring and bead sights, could not match. The radio equipment was compact, reliable, and capable of operating on multiple frequencies. Japanese aircraft radios were notoriously unreliable, and many pilots simply removed them to save weight. The most psychologically devastating aspect of the examination was not any single advanced system, but rather the overall impression of systematic excellence. Every component, every system, every detail reflected an industrial and engineering establishment operating at a level Japan could not approach. This was not a prototype or an experimental aircraft representing the best that American industry could occasionally achieve. This was a production aircraft, one of thousands built to identical standards, delivered to operational squadrons where it was considered routine equipment. Intelligence reports indicated that Vought Aircraft, Goodyear, and Brewster had all produced Corsairs, with total production exceeding 12,000 aircraft by war's end. Japan's entire production of all combat aircraft types for 1945 would barely exceed 10,000 units, and those would be plagued by quality issues and material shortages. The United States was producing one type of fighter in greater numbers than Japan could produce all types combined, and doing so while simultaneously building bombers, transports, and training aircraft in vast quantities. The engineers at Kasumigura understood mathematics. They could calculate power-to-weight ratios, wing loading, and thrust-to-drag coefficients. The numbers told an inescapable story. A Corsair with a full combat load could climb faster than a Zero at any altitude. It could dive faster. It could fly faster in level flight. It could take hits that would destroy a Zero and continue fighting. Its pilot was protected by armor that would stop machine gun rounds and small cannon shells. And behind every Corsair in combat were dozens more in the production pipeline, hundreds more in training squadrons, and thousands more being built in factories across America. Japanese fighter development had not stood still since 1940. The Navy had introduced improved Zero variants with more powerful engines and better armament. The A6M5 Model 52 featured the same Sakai 21 engine, but with improved exhaust thrust, thicker wing skins for better dive performance, and increased ammunition capacity. The A6M6C added some armor protection and self-sealing tanks, though at significant performance cost. Late war variants like the A6M8 attempted to address the power deficit by installing a Mitsubishi Kinsei engine rated at 1,560 horsepower, but only 2 prototypes were completed before war's end. Other Japanese fighters showed more promise. The Kawanishi N-1K-2J Shiden Kai was a genuinely excellent design that could compete with American fighters on more equal terms. The Mitsubishi J-2M Raiden Interceptor offered good speed and climb rate, but these aircraft entered service too late and in too few numbers to affect the war's outcome. Production problems, material shortages, and the destruction of factories by American bombing meant that improved Japanese fighters remained rare, while obsolescent Zeros continued to comprise the bulk of fighter strength. The examination of the captured Corsair occurred against this backdrop of desperate Japanese attempts to somehow close the performance gap. Engineers and designers knew what needed to be done: more powerful engines, better protection, heavier armament, improved systems. What they lacked was the industrial capacity, material resources, and time to implement these improvements at scale. The Corsair represented not just a superior design, but an entire industrial ecosystem that Japan could not replicate. Captured German technical information offered some hope. Japan received plans and samples of advanced German aviation technology, including jet engines and rocket-powered interceptors. Japanese engineers worked frantically to adapt Messerschmitt Me 262 and Me 163 concepts to Japanese production capabilities. Nakajima began development of the Kikka jet fighter, based on German designs. But these programs could not possibly mature quickly enough to affect the war's outcome, and they suffered from the same fundamental problems plaguing all Japanese aviation development: inadequate industrial capacity, material shortages, and American strategic bombing systematically destroying what manufacturing capability remained. The psychological impact on Japanese engineers examining the Corsair cannot be quantified precisely, but it emerges clearly from post-war interviews and recovered documents. They were not fools. They understood that Japan faced an opponent whose industrial strength exceeded their own by orders of magnitude. But understanding in the abstract differs profoundly from holding physical evidence in one's hands. The Corsair was that evidence 2,000 horsepower of undeniable reality that no amount of propaganda or wishful thinking could dismiss. The captured Corsair at Kasumigara represented just one aircraft among thousands lost by both sides in the Pacific War's final months. American forces recaptured it when they occupied Japan after the surrender in August 1945. Photographs taken by American personnel show the fabric-patched wings, the damage incompletely repaired, the evidence of Japanese efforts to understand and perhaps replicate what they faced. The aircraft itself likely ended up scrapped, one more piece of wartime wreckage processed through the massive post-war salvage operations that cleared battlefields and former military installations across Japan. But the knowledge gained from that examination could not be scrapped or forgotten. The engineers who studied the Corsair, who measured its engine and calculated its performance, who recognized the implications of its construction, they carried that knowledge with them through the war's final desperate months. And what they knew made the strategic situation even more hopeless than official pronouncements admitted. By spring 1945, Japanese aviation had effectively ceased to exist as a coherent fighting force capable of conventional operations. Pilot quality had collapsed as veteran aviators died and training programs shortened under pressure to produce replacement aircrew quickly. Fuel shortages meant that new pilots often received minimal flight time before assignment to operational units. Aircraft production continued, but quality declined precipitously as strategic bombing destroyed specialized factories and disrupted supply chains for critical materials. The Corsair examination occurred just as Japan fully committed to its final desperate strategy: organized suicide attacks. The Tokubetsu Kogeki Tai special attack units, known in the West as kamikazes, represented the ultimate admission that Japan could no longer compete with American forces in conventional combat. If Japanese pilots could not defeat American fighters and bombers in aerial combat, and if Japanese industry could not produce aircraft capable of matching American performance, then the only remaining option was to turn the aircraft themselves into weapons. The first organized kamikaze attacks occurred during the Battle of Leyte Gulf in October 1944. By the Battle of Okinawa in spring 1945, kamikaze attacks had become Japan's primary aerial tactic. Thousands of aircraft, including obsolete trainers, partially completed fighters, and even wooden gliders powered by rocket motors, were committed to suicide missions against American invasion fleets. The strategy inflicted significant casualties and damage, but it represented strategic bankruptcy. Japan was sacrificing irreplaceable pilots to achieve tactical results that could not alter the war's inevitable outcome. Zero fighters, the aircraft that had once epitomized Japanese aerial superiority, were relegated to this final role in large numbers. The A-6M5 and later variants were modified to carry single large bombs, typically 250 kilograms, for suicide attacks. The modifications were crude: a bomb rack hastily welded to the fuselage, centerline, sometimes armor removed to increase speed, often radios removed as unnecessary for one-way missions. Pilots received minimal training enough to take off, navigate to the target area, and dive their aircraft into American ships. The engineers at Kasumigara, who had examined the Corsair, understood the bitter irony. The same industrial capacity that produced 2,000 horsepower fighters in vast numbers also produced the radar-equipped destroyers, the proximity-fused anti-aircraft shells, and the carrier-based fighter patrols that shot down kamikaze aircraft by the hundreds before they could reach their targets. American combat air patrols, flying Corsairs and Hellcats, established defensive barriers dozens of miles from the fleet. Japanese pilots, many with fewer than 100 hours of total flight time, flying aircraft that were already obsolete in 1942, had virtually no chance of penetrating these defenses. When kamikaze aircraft did get through, and some did, through sheer numbers, if nothing else, they often struck ships equipped with damage control systems and redundant engineering that allowed them to survive hits that would have sunk Japanese vessels. American shipyards could repair battle damage in weeks and could replace lost ships faster than kamikazes could sink them. The exchange ratio was impossibly unfavorable, but Japan had no alternatives remaining. The strategy persisted because the alternative was surrendering without resistance, something military culture and political realities made impossible until atomic weapons and Soviet entry into the war finally forced capitulation. The Kasumigaura facility itself became a target of American bombing as the war entered its final phase. The airfield was struck multiple times during 1945, though damage remained relatively limited compared to the devastation inflicted on industrial centers like Tokyo, Nagoya, and Osaka. When American occupation forces arrived in August 1945, they found a facility still partially operational but depleted of fuel, spare parts, and much of its trained personnel. Lieutenant Toyoda Takago survived the war. In post-war interviews, he and other Japanese aviation specialists who had worked in foreign aircraft evaluation programs spoke candidly about what they had learned and when they had learned it. The consistent theme in these recollections was that anyone with access to captured American equipment understood by mid-1943 that Japan faced an opponent whose industrial and technological capabilities exceeded their own by such margins that conventional victory was impossible. This knowledge existed in tension with official pronouncements and military culture. Engineers could calculate performance specifications and production rates. They could examine American aircraft and recognize superior materials, sophisticated systems, and manufacturing quality. But translating this technical knowledge into strategic reassessment required political will and institutional frameworks that did not exist. The Japanese military command structure, divided between army and navy with minimal coordination, pursuing divergent strategic objectives, proved incapable of forcing realistic assessment of the situation. Even when realistic assessments were made, they often went unheeded. Japanese intelligence accurately estimated American aircraft production capacity by early 1943, but these estimates were dismissed as impossible by commanders who could not imagine industrial output at such scales. Reports from frontline units describing increasingly capable American fighters were noted, but did not fundamentally alter Japanese aviation doctrine or production priorities. The institutional momentum toward disaster proved unstoppable. The broader context makes the story of the captured Corsair even more poignant. By February 1945, when Japanese engineers were examining that Pratt & Whitney engine at Kasumigaura, the strategic situation was hopeless by any rational measure. Germany was weeks away from collapse. The Philippines had been liberated. American bombers were systematically destroying Japanese cities with incendiary raids that killed tens of thousands in single nights. The Navy had effectively ceased to exist as a fighting force. The Army was preparing for a final defense of the home islands that would result in millions of casualties. Yet the war continued for another 6 months. Hundreds of thousands more people died, Japanese civilians in bombing raids and the atomic attacks on Hiroshima and Nagasaki. Allied servicemen in continued combat operations, Japanese soldiers in futile defensive battles, and Japanese pilots in kamikaze attacks. The technical knowledge that Japanese engineers gained from examining captured American aircraft could not change strategic realities or alter political decisions about surrender terms and national honor. In the post-war period, some of those same engineers contributed to Japan's remarkable recovery and eventual emergence as a technological and industrial power. The lessons learned during the war about manufacturing quality, industrial organization, and the importance of matching design ambitions to production capabilities informed Japan's post-war economic development. Companies like Mitsubishi and Kawasaki, which had built wartime fighters, eventually became major players in global aerospace and heavy industry. But that future existed beyond a gulf of destruction and defeat. In February 1945, standing beside a captured Corsair in a hangar at Kasumigara, Japanese engineers saw only the present reality, an aircraft they could not match, powered by an engine they could not build, produced by an industrial system they could not replicate, flown by an enemy they could not defeat. The numbers told the story with mathematical precision. The R-2800 engine produced 2,000 horsepower. The Sakai engine produced 1,130 horsepower. The United States built over 12,000 Corsairs. Japan built approximately 10,900 Zeros total across all variants. American industry produced more of one fighter type than Japan produced of its most important fighter across 5 years of maximum effort, and the Corsair was only one of several advanced American fighter types in large-scale production. These figures represented not just technological superiority, but a fundamental difference in economic and industrial organization. The United States entered World War II with the world's largest economy and converted that economic power into military production at scales that surpassed all other combatants combined. American factories produced nearly 300,000 aircraft during the war. Japan produced approximately 70,000. The disparity extended to every category of military equipment: ships, tanks, artillery, trucks, ammunition, and all the supporting infrastructure of modern warfare. Japanese military planners in 1941 had gambled that superior training, fighting spirit, and initial surprise could compensate for American industrial might. They had believed that America lacked the will to sustain a long war across the Pacific, that early defeats would lead to a negotiated settlement favorable to Japan. The presence of that Corsair at Kasumigara, one aircraft among thousands, representing technology Japan could not match, and production capacity Japan could not approach, proved how catastrophically wrong those assumptions had been. The human dimension of this technological disparity manifests most clearly in the fates of individual pilots. American pilots who were shot down often survived, protected by armor, flying aircraft that could absorb damage, supported by extensive search and rescue operations. Japanese pilots who went down over water rarely survived. The Zero's lack of protection meant that combat damage was often fatal. The lack of effective rescue capabilities meant that pilots who ditched successfully often drowned or died of exposure before recovery. The mathematics of attrition favored the side that could protect its pilots and recover those who were shot down. By war's end, the average Japanese pilot had a fraction of the training hours that American pilots received. Quality had collapsed under the twin pressures of casualties eroding the instructor cadre and the desperate need to produce replacement pilots quickly. American training programs, by contrast, had expanded and improved throughout the war. By 1945, American pilots often had more flight hours before their first combat mission than many Japanese pilots accumulated in their entire careers. The technological gap that the Corsair represented was thus not merely a matter of horsepower and airframe construction. It reflected an entire system: industrial, production, pilot training, logistics, maintenance, and operational doctrine, all working in integrated fashion to produce combat effectiveness. Japan had created an excellent fighter and an elite pilot cadre in the late 1930s, but they had not created the supporting infrastructure necessary to sustain that excellence under the pressures of extended modern warfare against an opponent with vastly superior resources. Lieutenant Toyoda Takago, standing in that hangar in February 1945, examining an engine that produced twice the power of Japan's best, understood all of this. The Pratt & Whitney data plate was not just a piece of stamped metal. It was an epitaph for Japanese naval aviation, a technical specification that confirmed what many had suspected, but few had dared to acknowledge. The war had been lost long before the final battles, lost in the factories and design bureaus, and industrial infrastructure that Japan lacked and could never develop quickly enough to matter. The morning sun that had illuminated the Corsair's damaged wings in February would rise on an occupied Japan by August. The engineers who had studied that aircraft would witness their nation's surrender, the occupation, and the long rebuilding. Some would apply their knowledge to peaceful purposes. Others would struggle to reconcile technical expertise with the catastrophic decisions that had led Japan to war against an opponent whose industrial might they had briefly glimpsed through the specifications of a single captured fighter. In the end, the story of the Japanese engineers examining that Corsair at Kasumigora is a story about the collision between belief and evidence, between propaganda and reality, between what leadership claimed and what engineers measured. 2,000 horsepower could not be disputed or explained away. The aluminum panels and armor plate could not be dismissed as American trickery. The sophisticated systems could not be ignored as irrelevant to combat effectiveness. The war would continue for 6 more months of destruction and death. But for those who understood the numbers, who calculated the ratios and recognized the implications, the outcome was already determined. The Corsair proved it with mathematical certainty, written in horsepower and production statistics, and the simple, undeniable fact of American industrial superiority. Victory required more than courage or training or tactical skill. It required the economic and industrial foundation to sustain modern technological warfare. Japan had committed to a war it could not win against an opponent it could not match. And in a hangar at Kasumigara, examining an engine too powerful for their factories to build, Japanese engineers held the proof in their hands. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.